let's see how to perform the segmentation analysis using the SCHELI plugin. So we go on plugins, we select SCHELI and then segment. It will open up this window with a lot of information. So uh, first the paths, the input directory, so the folder containing all of the images that we want to use. I have already created it here, and as you can see, there are a lot of different images, really heterogeneous, with a lot of different colors and shapes of the nuclei. Um, and then the output directory, so where we want the resulting analysis to be. For clarity, I have already created everything here. This is not something mandatory, but it it's much easier to follow everything if you do uh, the same configuration of your folders. So let's see the settings. This is the scale. It's optional. You can also put it as 1. I know from my microscope that it is 0.58 micrometers for each pixel. Sorry, with a dot. And then let's see the other panels here in this setting window. This is the low and high percentiles. These are thresholds used by the StarDist plugin. Mm, Usually, they will not influence that much your your analysis, especially the high percentile does not influence that much. The low percentile, if you l- put it at 0, it will work fine with most hepatocytes, but in case of infiltrate and other really close together nuclei, it will lose a lot of nuclei and get a lot of false negatives. If you get it too high, on the other hand, you will have too many false positives. So be careful. The tiles are simply for a RAM, so a memory allocation. If you have a really, really big image that's, I don't know, a panoramic, a stitched image, then the computer might struggle to analyze it all of it at once. And so we can divide it into many tiles and simply analyze it bit by bit, and then stitch everything together at the end. These thresholds are, again, the 35 nuclear threshold is another StarDist threshold used like a measurement of how certain our model is when selecting a nucleus. So this means that if it is at least 35% certain that that spot is a nucleus, well, it will assign it as a nucleus. If we put it at 100%, we will have 0 nuclei because it's never 100% certain of anything. If we put it at 0, everything will be a nucleus. This is, in my preliminary analysis, one of the sweet spots for liver analysis. The background threshold instead is a measurement of how bright is your background. If it's pure white, so it has a value intensity of 255, then you should put 100%. If it's a little bit darker, you should lower this down. So this is a measurement of 0 to 100. You can also measure um, the pixel values of your darkest background spots, and then simply divide it by 2.55, and you will get around the value that is most suitable for your photos. Sizes here are calculated using the scale, so if you do not set it, it will be just in pixels or pixels squared. In this case, I selected 60 and 3 square micrometers for the minimum size of the vessels and minimum size of the nucleus, and then a really high number for the maximum size, since I do not want to exclude anything. The neighbor radius is simply when calculating how dense the nuclear distribution is around our analyzed nucleus. We set a range, we draw a circle, and we simply count how many neighbors are in that circle. This is simply the radius of that circle right there. And it's used mostly to help us identify the infiltrate, which will have a lot of nuclei right next to it. The colors, this will not influence in any way your analysis. It's just a simple graphical interface created in the preview image. And so you can choose the colors that are most aesthetically pleasing for you to display the analysis at the end. The output allows us to choose between the US and EU format when we export the CSVs. So if we use the US format, we will have some values separated by commas, and that use a dot as decimal. If we switch to the EU format, we will have a semicolon, a separator, and comma used as decimal. Then we can select what do we want to save. If we want to save the rows and maybe do some custom analysis after that, we can check this one. The previews are simply the images produced as a reference to see how well the segmentation was performed. So it's just a graphical representation of everything. The averages is a CSV file containing the average for each image. So, for example, you will have the average area of each nucleus, the average cytoplasmic area, the average mean value, and so on, which will be calculated arithmetically. So, for example, if you want to measure the true average intensity value of of the cytoplasm, for example, you want to see how intensely it was stained with hematoxylin. This average is simply counting each cell and then summing them up and dividing by the number of total cells. So a really small cell with few to no cytoplasm at all will influence to the average as much as a really big cell. So if you want more precise analysis, you should do it by yourself. This is simply to have everything ready and have a preliminary analysis. Then the most important file for the classification, if you want to also perform that later, is the save individual cells. This will save for every single image a CSV containing a row for each nucleus, a row for each cytoplasm, and a row for each cellular row. Then we have the ignore border vessels. This is simply used when calculating the closest vessel to the cell. If we ignore it, then all vessels or white rows that are touching the border will be considered as being simply background and not vessels. If we uncheck it, it means that we are certain that in our image there is no background and all um, white pixels assigned as being vessels are truly vessels. So be careful when taking your images to have them all conforming to the same standard. In the end, the debug messages are simply a log. If anything goes wrong and you do not know why, um, you can check it and see the full log. So here's is an example. It will create the ROI for calculation. It will create the progress bar. And since we checked the debug checkbox, we also get this, where we can see uh, what the code is doing in real time. Uh, for the analysis, I found out that it really depends not only on the number of cells in the image, but also on the number of total pixels. Also, since the image gets converted at the start mm, of the plugin, gets converted to a TIFF, it does not matter the compression. So if you want to compress using JPGs or PNGs, it will not affect the total time it will take for the result. So here you can see in real time, it does not take that long. It might differ from device to device, but it usually does not take more than half an hour for whatever analysis you have to do. Um, and that's pretty much it. Let's see now the logic behind the SCHELI segmentation plugin. We start with a normal hematoxylin eosin image. In this case, since there were a lot of erythrocytes in this particular vessel, we decided to enhance the process of segmentation by filling in all of the vessel with white pixels. This is an optional step, but it increases the accuracy of the segmentation. The first step involves the StarDist plugin, which segments each nucleus, assigning it to a ROI. And then the center of mass of each one of these nuclei is used for the Voronoi tessellation, which is shown in this GIF, and which creates this kind of weird polygons, which are simply the sets of pixels which are closest to the center of mass of the nucleus. The resulting image looks like this. So each one of these polygons is considered to be a cell. We also add the segmented vessel and we get the final result here. The elements bordering the edge of the image are shown in gray and black, and in the final measurements are have a custom label to allow during the analysis to be excluded, since both shape and size might differ a lot, as well as having more false positives and false negatives near the border. And that's it. This is the segmentation.